So the next section, 8.3, is now we use this kind of operator to solve the eigenvalue problem. So basically, now we get rid of all that. So basically, you want your eigenvalue problem is L y equals to lambda y, right? And solve for lambda, and so the one way to do it, obviously, go back to what we did in chapter 6, in expand the function and the operator of a normal basis and reduce that to a matrix differential matrix eigenvalue problem. For this differential operator, there's a little bit difficulty that the matrix is infinite dimension, because you have the basis has infinitely many bases. So when you do a matrix, reduce that to a matrix problem, you get some difficulty to deal with infinite dimension, infinite rank matrix. So what doesn't mean it cannot do. I mean, you probably can find a way to get around that. But another way to do it is to solve the differential equation. So that combining the lambda to here just now becomes a new differential equation. You try to solve it and see if you get a reasonable result. And in some cases, you have a lambda that any lambda will give you a reasonable function. So lambda, so your eigenvalue becomes a continuum. So any real value will satisfy that differential equation and satisfy the boundary condition. So that is possible. But in some cases, the boundary value will make sure that you only have certain discrete lambda that satisfies the boundary condition, and so that imposes a condition on lambda, and that is also possible. The example 8.3.1 is on the Legendre equation, and then the 8.3.2 is on the Hermite equation. So the Legendre problem, we'll probably talk more about that in a later chapter. But I actually have a video on my YouTube page that I already worked out 8.3.1, but I didn't work out the 8.3.2. Maybe we'll work on. They both are very similar. The 8.3.1 is a Legendre polynomial which define over the domain -1 to 1. So and we try to solve the differential equation using series solution that we learn how to do it, and then we test for convergency. And for the Legendre equation, the solution is always convergent if x is less than 1. That is possible. So for any lambda, the Legendre equation, the solution is convergent in the interior of your domain, but not on this is the convergent, but at x equals to 1 becomes divergent. But for general lambda, that's the first example. We show that the series solution will show that this is the case, and so that the conclusion is if you have a problem that doesn't involve the boundary term, the 1 and -1, just the interior, then any lambda is fine. So now you define the solution of the differential equation has infinitely many terms. That's a power series of infinite power series. But if the problem involves the boundary term 1 and -1, then that series solution is not valid unless the series truncate at a certain terms. After a certain term, all the coefficient becomes 0, and that is possible from the recurrence formula if lambda equals L plus 1. L is start from 0. So you have a general choice of L, the 0, 1, 2, 3, and L is 0, 1, 2, 3, and then lambda becomes whatever this function L times L plus 1. If this is satisfied, then obviously, because it's truncated, there's no convergency. I mean, this is just a polynomial. We just evaluate that, and so that make the solution valid over the whole range, from -1 to 1. So that's example 8.3.1. But I'll skip it for now, and we'll probably come back to when we talk about Legendre polynomial later in chapter, right? One of the chapter later. Okay, and then example 8.3.2 is similar, a little different, but there's a similar discussion, so we'll work that out as an example for this section. The operator is L times Y is minus Y double prime plus 2x Y prime and equals to lambda Y. Okay, and so that is your eigenvalue problem. So compare with this form, so P sub 0 is -1, right? And P sub 1 is 2x, right? And we can check that the PCO prime is 0, obviously not equals to P sub 1. So you need to define your scalar product with a weight function W. So W is using our formula, I think it's 1 over P sub 0 exponential function P sub 1 over P sub 0. You need to define that. You can work that out. This is -1, so minus, right? And then exponential function minus integrating qx dx. Right. And then let's work that out. This is to integrate the x squared over 2 and cancel 2, so minus x squared. Right. So obviously your W cannot be negative, so you, but there's a choice. You always can multiply by a constant because the previous discussion doesn't matter, whatever the whatever constant in front of your W, still the previous discussion still still goes through. So you can multiply a negative constant to make it positive definite, right? So that you choose. Now you redefine your W. W is e to the minus x squared. That is for the Hermite equation. You need to define your scalar product with an exponential function. Exponential minus x squared. So that scalar product is 8.28. So with this W. Okay, but in solving the differential equation, actually you don't need the W yet. So the discussion of this is just for later use. If you wanted to solve for your eigenvalue and define your scalar product or normalize your W or normalize your state, you need the W, right? But for us, we'll just solve it. Let's try to find a serious solution for that one. So just follow the same rules of y as sum over j, a sub j, j from 0 to infinity, x to the j plus s, right? That is y. You need the y here, you need y prime, actually x times y prime, and then y double prime. So you need to work out the y prime. J plus s times a sub j plus s minus 1. And you need y double prime. J plus s j plus s minus 1 a sub j j plus s minus 2. Okay, so you need this one. And you need x terms that you don't have just at y prime, so you can multiply x here. Get rid of this. So both these terms have the same form, but not the y double prime term. So what we can do is shift the j, and so this j plus s minus 2 become j plus 2, j plus s, which means what you can say is j prime plus s. The j prime is j minus 2, right? So what j is j prime plus 2. J is j prime plus 2, j plus 2, j plus s plus 1, j plus 2, right? X plus s. And then you just start with j prime is for minus 2. Right? So that is y double prime. Now you every term has the same form. So you just substitute all of it with this equation, and so you have two extra term minus 2 and minus 1. Otherwise, you have the summation from j from 0 to infinity, and everything proportional to x to the j plus s. But then you have this term, this negative term, negative plus s plus 2, plus s plus 1, and that proportional to a sub j plus 2. And then you have two terms, this one and that one, that proportional a sub j. Two times this one, 2, j plus s, and then minus lambda, a sub j. Represent proportional x to j plus s. Okay. And then the two extra terms, you have j is minus 2, j is minus 2. Right? Minus 2, so you get s times s minus 1 times a sub 0 x 0 s minus 2. Right. And then plus J is minus 1, S plus 1, and S. J is minus 1, so S plus 1, S is J is minus 1, this is S. A sub 1, S minus 1. Okay. So the initial condition is from that the first, you assume A sub 0 is not 0, so you have two solutions. S is 0 or S is 1. Did I get it correctly? Why your textbook at minus 1? Can you see why what I did wrong here? J is minus, oh yeah, this is minus 1. J is minus to S minus 1. Okay, that is more or less. Yeah, y double prime is here. Yeah, right here, right. Right, this is from 9 double prime, yeah. But, it turns out that you just set those to 0, so positive, negative doesn't matter, but anyway, it's negative. So, so what you need is you want to set that to 0. If A sub 0 is not 0, so they have two choices. Either S is 0 or S equals to 1. Okay, and so there are two solutions, and for S equals 1, actually both terms will be 0, automatic 0, so that is fine. So that is one choice that get rid of both terms. So that in that case, you can keep A sub 1 to non-zero, but usually you don't want that. You want two independent solutions that because this recurrence formula, we set this to 0 is, or J is jumping by 2 always. So it has the odd or even symmetry. And so you choose A sub 0 non-zero, then you don't want to start with mixing the A sub 1 non-zero. So you can set A sub 1 to 0 in that case. For S equals to 1, that is 0, obviously. And that this coefficient is non-zero, then you must choose A sub 1 to be 0. So you have basically two independent solutions. So that's one way to do it, choose S0 and S1. The other possibility is you just choose S equals 0. But then for the first solution, you set A sub 0 non-zero, A sub 1 to 0. So you get one solution. But the other solution is still S equals 0, but you choose A sub 0 to 0. But A sub 1 is non-zero. Then you generate the other solution. So the first solution, we start with, go back to your choice. If S equals 0, you always start with x to the j, which is start from 0. So, right? So if S equals 0, and if A sub 0 is non-zero, you start with A sub 0. Then you got all the even power of x. So that's your choice. But if you set A sub 0 to non-zero, but A sub 1 non-zero, this will start with j equals to 1. So you start with x as is 0. You start with linear terms in the power of x. You got x and the x cube and x fifth term. Yeah. You get all power of x by doing that. So, so either way is fine. That is the second case, setting A 0, 0, A1 non-zero, exactly like the setting S equals to 1. And then we call A 0 non-zero, A1 is 0. That two solution will be identical. So either way, you can do that. And if you do it the first case, set S equals 0, and then the iteration recurrence equation will be the same for both series, right? And let's just do it this way. Set S equals 0. So this recurrence form, and the recurrence relation will be A j plus 2 equals to 2j, s is 0 minus lambda times a to a sub j, and divided by this factor will be j a plus 2 times j plus 1. That would be the recurrence formula, and that is that's equation 8.29. All right, so that is basically a series solution. Now the idea is you want to test convergency, whether the solution is well behaved, and we can look at the convergency by the ratio test, right? And the ratio test is basically this divided by that and multiplied by x squared. So aj plus 2 divided by aj multiplied by x squared equals to basically just the coefficient 2j minus lambda x squared a plus 2 a plus 1, right? And then you want to choose take the limit that j goes to infinity, right? When j goes to infinity, lambda is finite, so that ignore lambda, ignore 2 and 1, so you have 2j divided by j squared, so it tends to 2x squared over j. Right. I think so. Yeah. But that's fine. Yeah. Okay. And obviously that would be convergence that would tend to 0. So all finite x. So for the whole range of x except obviously infinity, then it's convergent, right? So the convergence is fine, but then you realize that by this kind of iteration, then the function, the asymptotic behavior at large x, this is like a function exponential x squared, right? Because exponential x squared is just like sum over the 0 to infinity. You have x squared to the j power divided by j factorial, right? And the ratio between the two terms is exactly the same as the limit. So you have x squared and then the j. Yeah. The j and j plus 1 you divided by j, right? Right. So a for this one, for the successive terms of a equals 2 over aj will be x squared. You have j plus 2 j plus 2, and then the other one is j plus 1. Actually, j plus 1, yeah, this is j plus 1. Because it's always jumping by 2 for this one. It's only jumping by 1. The j, right? So this is successive term is x squared. So we have j plus 1 factorial divided by j factorial. You cancel the rest, becomes j plus 1 or 1 over j. And this is factor of 2. I guess you need to redefine your j, redefine your j to match it. because you always jumping by 2, right? So like for this case, depends on whether it's odd or even. So j equals to n, or whatever n is. Now start from 0 to infinity. The j will be 2n. The 2n, so this is x squared over n. Right. So they have the same asymptotic behavior. So it means this kind of iteration will be like have the asymptotic behavior of exponential x squared for large x. And that means it's going to infinity. It's not singular at any finite point, but it's going to very large. That make the solution not well behaved for many physical problems. Okay, so that that is not very good for application. And obviously you have this w that has the exponential minus x squared, but you remember the scalar product, so f and g now have this now it's minus infinity to infinity, and you have a w, so you have x squared and g, right? And if both f and g's are solution for eigenvalue problem, then both have the exponential x squared, and then you have exponential minus x squared or the w factor. I mean, asymptotically, they behave like that. So it means the scalar product is not well defined. It's just blow up. The whole thing blow up with this kind of asymptotic behavior. So that's not good. You cannot define your scalar product even with this w. And so the solution is to truncate the series, just like what we mentioned, the general polynomial, the Hermite solution. We need to truncate the solution, and what the result will be your so-called Hermite polynomial, at least proportional Hermite polynomial. And the idea is that if somewhere along the line the numerator is 0 at a certain point, then say you set a certain point up to n, n. If for a sub n, j equals to n, this is 0, then a to n plus 2 will be 0. You put n plus 2, a to n plus a sub n plus 2, n plus 2 here, then n plus 4 is also 0, and all the coefficient later will be all be 0, so you truncate your series. And the idea is for this equation, there's obvious choice because your j is going from 0 to infinity. The j is 0, 1, 2, 3. So this is always a even number. And so if you choose lambda equals to n or something, I think that's suggested by a textbook. Lambda. I mean, your textbook say 2j, but I mean, j is your iteration parameter, so you probably want to choose, say, no room in here. So let's just get rid of that. So you choose lambda equals to 2n, right? Then the coefficient will be all will be finite. I mean, the only have finite up to 2n. So you a to the 2n, but you multiply 2j minus 2 up to j equals to n. Well, you get 2n minus 2n will be 0. So a, that means a to n plus 2 will be 0, and so on. So only finite up to a sub 0 to a sub 2, all the way to a sub 2n. Right. If you choose lambda equal to 2n, then you have all this term non-zero, but the rest of the coefficient will be 0. Okay, and now for this truncation now, you cannot use the method I mentioned previously. You set S equals 0 and choose A sub 0 to 0 and A1 non-zero. That would work if the behavior of your equation is a solution is well behaved, but not for this one, because J, we start from 1, you have 1, 1, 2, 3, 4, right? And you start from A sub 1. Then you have A sub 1 and A sub 3, A sub 1, A sub 3, A sub 5. The J, this is your J, right? J. Well, I guess you can do that also, because J is not, I mean, 2J is an even number, but J is still just integer. So it doesn't matter. So you can still choose. So this is for the first case. For the second case is A1, A2, up to, that's A is N. No, A is 3, right? J is 3. Well, that is still fine, yes. But, but J is lambda over 2. A. I mean, it's the iteration equation for S equals 0 is still the same. You just start from 1 and then get 3, and like if it's 1, then lambda is, if lambda is 2, then you have 3, right? Oh yeah, I think I wrote wrong. 2J equals to 2 lambda. So it's actually only up to n. It's only up to n plus 2. Right. And likewise, this is, if you choose this for A1, A3, it's also choose A to n. Right. The n will stop at the odd number. Right. And then an plus 2 is also odd number. So that is still true. But you start with an odd number if you do it this way. If you choose S equals to 1 and set A0 0, A0 non-zero, A1 is 0, then you need to change your iteration, relation with S equals to 1 here. But either way is the same. So you actually can solve it this way. Right. See, okay, a little confusing because because you're always jumping to, J is always jumping to the coefficient, but the n here, lambda n can be any integer. Lambda is 2n, lambda is even, but n is a integer, so either integer, either even or odd. Okay, it's okay. So that's this example, and after you truncate that, so it depends on n, so you have this finite number of them, then for higher order, n is high order, you have more and more terms of the polynomial, the order of polynomial becomes higher, and that's what we call Hermite polynomial. And we won't talk about specifically about Hermite polynomial. There's another chapter that we skip that talk about that. But either way, it's also a very useful polynomial. Okay, so that's the I think that's all for 8.3. Okay, any question? No, no.